Okay, let's start. So this is lecture 26 and we are going to continue discussing the Higgs mechanism. So were there any questions about last time, or what we did last time? All very clear? Okay, so one announcement is that I revised all my notes, not all my notes, my last two lectures notes to fix all the factors of square root of 2, which were very annoying. I think I finally found a set of conventions that works for me. I hope it works for you, and if there are still errors, obviously you need to tell me. So please don't hesitate to do that. So basically the problems were all with the complex case. The reason is that a complex boson is normalized in the kinetic term as del phi star del phi, but a real one is 1 by 2 del phi, and that's was tricky to get everything straight, but I think I did. So now today what do we want to do? It's very obvious. Last time we discussed abelian gauge theory coupled to a charged scalar field. That theory is called scalar electrodynamics, and we showed that if that scalar field has a symmetry breaking type of potential, then the resulting theory undergoes a Higgs mechanism. What would have been a Goldstone boson without the gauge field disappears, and the gauge field becomes massive. And one real boson is left over. People asked, so one question that I got asked last time was that technically there's a global and a local symmetry, because the global U1 symmetry should be distinguished from the local one, which falls off at infinity. That's true, and it's the global one which gives you a Goldstone boson. The point is that now that you have a local one and with it a gauge field, the gauge field eats up that very Goldstone boson. That's why there's no Goldstone boson at the end. Technically, if you go through the formal proof of Goldstone's theorem, you see that it actually doesn't work in the presence of a local symmetry. So but the reason it doesn't work is that yes, there's a Goldstone boson, and then it just gets swallowed up.
We still broke the global part.
We still broke the global one spontaneously. So it's also still there, but in the spontaneously broken form. That's right. I think that's a good point. So the global one is present in spontaneously broken form, and the local one is present in Higgs form. It's just that we use slightly different words, but now I realize everybody calls it spontaneously broken gauge theory, including Weinberg, who I admire as the world's biggest ever expert on this subject. So I think I should stop complaining about it. If you want, you can call it what you like, but it's Higgs mechanism. Now the point is that Higgs mechanism is very nice, and in the abelian theory it actually does have applications in condensed matter physics. And I don't have right now anything to tell you about that, but both spontaneous symmetry breaking and Higgs mechanism arise in materials, and they explain various things. So for example, phonons, which are vibrations of some system, come from the spontaneous breaking of translation invariance by the presence of a lattice, and that's why they are light. So one important point is that a Goldstone boson has to be exactly massless as per Goldstone's theorem, but if the original symmetry is sort of approximate or something, then they may not be exactly massless, but they'll still be light, relatively light. And this is important because when we study any theory, we always study the lightest excitations of that theory, because they are the ones that small amount of energy can produce. So there'll be many of those compared with the heavy excitations. So now I'm trying to set up for you a guest lecture by somebody, hopefully one of my colleagues here, on the condensed matter usage of both spontaneous symmetry breaking and Higgs mechanism. It's a very beautiful subject, and it will help you to see the why this is a broader thing than just in particle physics. However, in particle physics, where we work not in a condensed matter or in a solid state, but rather in vacuum state or in empty space like an accelerator, we certainly don't want either spontaneous symmetry breaking or Higgs mechanism to take place in the abelian theory. Because if spontaneous symmetry breaking just takes place, which has nothing to do with charged particles, then there'll be a Goldstone boson. That's not something we experimentally see. And if on the other hand we couple the photon to that and make it a Higgs mechanism, then the photon will get a mass, and then we won't be able to see light coming from the sun or from anywhere, maybe not even from the from these light bulbs, because the photon wave will attenuate at a distance of order inverse mass, and that's not compatible with experiment. So we don't really, in particle physics, we don't want this to happen in a abelian theory, but we are perfectly happy if it happens in a non-abelian theory. So that's what I'll discuss today. So basically, Higgs mechanism in non-abelian or Yang-Mills theory. And for this, let's set up the Lagrangian. Everything is stuff that we have done before. For now, I'll take this to be an SUN theory, but as soon as I start to do any calculation, I'll make it SU2 so that we can do the calculation. It's not that hard to do with SUN, but it's very, very transparent with SU2. So this plus d mu phi dagger I d mu phi I. This is a covariant derivative, so it's a standard thing. We've discussed it when we coupled Yang-Mills to matter. The only problem which keeps me awake at night is that I think I chose a different convention for the non-abelian covariant derivative compared with the abelian one. I'm not even sure that's true, but as I recall, the covariant derivative is del mu minus ig a mu. So okay, we've discussed this covariant derivative many times, but in particular we had one whole lecture or part of a lecture on coupling Yang-Mills to scalars and fermions, and that coupling had to be done with this covariant derivative, which had a very beautiful property. The property was that if phi goes to u phi, where u of x times phi, and a goes to, so phi, this phi is a vector, so I don't put anything under it, and a goes to I upon g u inverse del mu u plus or minus, this is a plus u inverse a mu u, right? This is the gauge transformation on the combined Yang-Mills and matter system. Yes.
So it's plus if it is u a mu u inverse.
Ah, really? And this also?
Yes.
That's what I
No,
read?
sir.
Okay, let me check. It's of course a nightmare which I'm always scared to even look at. But yes, u a mu u inverse, exactly. Thank you. And actually I should have not even made this mistake, because you can also see why I chose this convention, because you see this a mu is hitting a phi, right? Phi is going to become u phi. This u inverse will cancel it. Okay, so the u will come on the other side of a. So this term a phi will go to u a phi. This is more complicated, but what will happen is that when phi gets u phi on it, del mu will act on phi or on u. When it acts on phi, then u is on the left. When it acts on u, it gives a new term which is to be cancelled by this. That's exactly why gauge fields are needed to restore gauge invariance, because when the derivative acts on the gauge variation due to its space-time dependence, that is the term which is extra. Okay, if u was constant, that wouldn't be there. This also wouldn't be there. Gauge fields always have an inhomogeneous term because of that. If you are not aware of these things, you need to just go through the notes very carefully. But thanks for correcting my conventions. And now this derivative has this nice property that if phi goes to phi prime I, which is u phi, then d prime mu of phi prime, which I mean is d mu of a prime on u phi. I hope you understand what this means. So a goes to this, u goes to this, so I'll say that phi goes to phi prime equals this, and a goes to a prime equals this. Okay, so after my gauge transformation, my d phi term has gone to d prime phi prime. So phi has changed to phi prime, but d has also changed to d prime because inside it there was an a that has to be changed to a prime. Okay, and this has the property which is proved in the notes that this is equal to u times d mu of the original phi. In other words, the u just comes out. This is a very crucial relation. Okay. So we'll use this later on. So let me write this relation here. I'll write it in the following form, that d phi, I'll take u to the other side. So d phi is equal to u inverse d mu of a prime u phi. And as I said many times, if you have the slightest hesitation about why this is true, you need to work it out very, very carefully, because this is absolutely the crux of Yang-Mills theory. Good. So now let's get on with all these definitions. We need to finish writing the... So this definition I'm going to erase. This is absolutely standard. And we have yet to put the potential of spontaneous symmetry breaking form and then analyze the theory. So the potential I'm going to add is minus lambda phi dagger I phi I minus a squared by 2. So my new convention is that for complex fields it's always a squared by 2. When I take this and expand it in terms of 1 by root 2 times the radial variable will have a expectation value of a rather than a by root 2. So this is my thing squared. This is my symmetry breaking potential. This is the standard one, and we're just always going to use it in this form, which is very convenient. And now we have to analyze this theory. So again, this is given to you. It's manifestly gauge invariant, right? Because well, this is gauge invariant by the rules of Yang-Mills theory by itself. This is gauge invariant obviously because what is the gauge transformation? The gauge transformation is that phi I goes to e to the I lambda a t a lambda a of x t a I j phi j. So this is u for an arbitrary lambda. And of course, you can see that this term is trivially invariant, gauge invariant, because when I write phi dagger phi, so after a gauge transformation, phi dagger picks up this factor on the right and with a minus sign. And phi is this. You can call this b times phi. Well, those middle two terms cancel. So phi dagger phi after gauge transformation goes to that, which is just equal to phi dagger phi. So there's no change in phi dagger phi under gauge transformation. We have seen this in the Abelian case a few thousand times because phi star phi is invariant under any phase transformation. We have done that calculation many, many times. Is the generalization of that. What would have been unclear is why this term is gauge invariant. But it's exactly due to the property of d mu phi that I've written here, because from that I see that this goes to U inverse d mu U. Okay, so probably I have to use it in the other form. Let's see. So this, after the gauge transformation, goes to d mu prime phi prime dagger I, d mu phi I. Again prime, everything is prime. And this is d prime phi prime. This thing is phi prime. So it's equal to u d phi. So this is equal to u d mu phi. And what's the dagger of u d mu phi? It's d mu phi dagger u inverse. Because this is unitary, it cancels. That's why this is invariant. People are looking a little surprised, and I think that means that that section of the discussion did not go through very clearly, but now I hope it's clearer. I emphasize again, this is absolutely crucial. This is why this Lagrangian is gauge invariant. Unless it is, there is no point in us doing anything else. Okay, but it is. So let's proceed now. Well, the steps to study the Higgs mechanism start in the same way as the steps to study spontaneous symmetry breaking, namely to identify the classical vacuum, which in this case satisfies phi dagger I, phi I is equal to a squared by 2. Now we have various choices. As we did in the single complex field case, we can write the field in its Cartesian real coordinates. We can just take each component of the field and write a real and imaginary part and just keep writing them. And then we can put, we can take a wave. So we could take the wave to be phi I classical equals 0, 0, 0 and a by root 2. And then if we want, we can define the full field to just have some field eta 1, eta 2 up to eta n minus 1 and sigma, and they are all complex because phi is complex because this is a unitary model. So I could do that. Before I do that, let's look at this classical vacuum. We've already established that this vector is invariant under SUN minus 1 acting on just these components. We established that with the ON group, but it's the same with the SUN group. SUN rotation, SUN minus 1 rotation will only act on the first n minus 1 components and won't act on that. And so that's the unbroken group. So SUN is breaking. This wave breaks SUN to SUN minus 1. Again, it's a theorem, though not maybe as obvious as it was in the orthogonal case, that any wave which I give, I could just put some number in each of these entries such that the sum of squares is a squared by 2. That would be a very general vacuum value. But any of those by an SUN transformation can be pushed into the last place and also made real. So therefore, this is the most general vacuum value. And so this theory always breaks SUN to SUN minus 1. There can be more complicated theories where the choice of vacuum may tell you what breaking takes place. Like with this vacuum, SUN breaks to that. With some other vacuum, SUN breaks to something else. But in this case, it's unique. Okay. Now, we don't want to do this Cartesian parameterization, as I'm calling it, calling these eta 1, eta 2, eta 3, for the simple reason that we already saw that those are not the real Goldstone bosons. Those are tangent to the space of vacua, but they are not the angular variables. Right? You remember that we had this discussion. So that's not a good parameterization. What would it be if I wanted to do it? Just to write it, would be phi a is eta 1 up to eta n minus 1, a plus sigma, with all these fields being complex. These are n complex fields, and these are also n complex fields. And now the vacuum value of all of them is 0. Usually we do it this way. So the cleverer thing to do is to write phi I as 0, So I'll write it as a column vector 0, 0, a by root 2, a plus sigma by root 2 times e to the I theta a T a. So this is a parameterization of phi, and it's very similar to the angular parameterization for the complex field, where this was the phase and that we just had the magnitude. Now we have a vector and we have a generalized phase. It's still a phase, but it's a matrix. So this times this means this matrix Ij and this column vector J multiplied as a matrix into a vector. So this is a parameterization. So I should argue that it's always possible to choose this. That is, for any phi, which is a n component complex vector, I can parameterize it like this. Okay. And actually I have already given you the argument 1 minute ago. I said that by an SUN rotation, I can always get any phi into the form with a by root 2 here. So I just take a phi and I bring it into that form, and then I just perturb around that, and then I use that same SUN rotation to bring it back to general form. Okay, but the only problem is that, well, this is one field and these have to be 2n minus 1 generators. We discussed it last time. And what are these? These are the generators of SUN which are not in SUN minus 1. It's almost obvious, because if they were in SUN minus 1, the action on this would be trivial, right? Because they would just permute the first entries, which are all 0, so it would do nothing. So the only technical problem in doing all this is that I should move the SUN minus 1 things to the right so that they act trivially, but then these matrices don't commute, so it's a bit of nightmare to do it in precisely. Okay, but conceptually you can understand this. But now what we are going to do is, this much is in generality. The claim is it can always be done, but I am going to now restrict to n equals 2, which means my group is SU2, and in that case phi I is just equal to e to the I theta a sigma a by 2, 0 and 1 by root 2 a plus sigma of x. These sigmas are Pauli matrices. We know what they are. There are 3 of them. So the total phi's were 4. It was a 2-component complex vector. Let's write it like this. Both components are complex. That's what these original phi's meant. Phi I. So there are 4 real components inside this. On the right there are 3 thetas and 1 sigma. So 4. So this is how I've parameterized my phi. And this parameterization makes everything go very easily. I could do this parameterization even in the non-gauge case, the global symmetry case. I mentioned it already once, but now I'm going to work it out in the gauge invariance case. Yes?
One more symmetry I think is O to N, but we are assuming that other fields, other interactions will not satisfy.
That's right. We are just assuming that. And that's true in the standard model, for example, where we do have an SU2 and it's not extended to O4 because of coupling to other things like fermions. Okay, good. No, this I do not want to erase. This we are going to keep as long as we can. To make my life easier, I'll write this over here. So that's my Lagrangian. Okay, now I want to insert this into this. First thing is, this is I'm replacing the field phi by those things, so nothing happens to the first term, which doesn't depend on phi, it's just the Yang-Mills term. So I just copy it down. Okay, so that's done. We'll come to this term, but let's first look at this term. What happens to this term when I put this in? So for simplicity, I'm going to write this as e to the I theta a sigma a by 2 times capital sigma So I, where sigma is that. So this thing I'm just renaming as sigma I. It's a two-component SU2 vector with one component being 0 and the other component being A plus sigma over root 2. Just for notational purpose, I'm calling it capital sigma.
Sir,
Yes.
sir, can I write here phi I as r and e to the I theta?
See,
That-
phi I has 4 components. So what do you mean r e to the I theta?
I was thinking, can we?
Good.
Yeah.
So actually, I suppose we could have done that. We have done something a little different. We have put everything into the last component. So if you see, it's a vector. So what does it mean to write a vector as r e to the I theta? R is one thing, right? Is a one radial direction. So in a way, we've done that, but we've picked that direction to be in the second entry. We just removed it from the first entry. So so this is the way to generalize r e to the I theta. So capital sigma. So phi therefore is equal to e to the I theta a sigma a by 2 sigma. And I write this like this because this is a matrix and it multiplies sigma. So this matrix ij times sigma j has a free index I, and that's the vector you get after doing that matrix multiplication. Clear? Okay. So now if I put this in the last term, what happens to phi dagger phi? We did this, I believe, a few seconds ago. Invariant means? What is it in terms of thetas and sigma, capital sigma?
Sigma
Phi is
dagger-
equal to this
sigma-
times sigma.
Sigma dagger I.
Exactly, that's what I know. Thank you. That's simple. Okay? Good. So therefore this term is minus lambda sigma dagger I, sigma I minus a squared by 2. Okay. Does it depend on the theta fields? Do you remember something similar happened in the complex case? The potential didn't depend on the theta parameter. In R and theta decomposition, the potential just didn't depend on theta. It only depended on that eta, R, and which became eta. Same thing. So this is done. So Goldstone boson is not visible here. That's good, because if there was no gauge symmetry, Goldstone boson would have only derivative coupling, so it better not be visible in this term. So it's not visible in this term. So that term we can forget about. Now we have to ask, what does this do in the middle term? Okay, and now again we are going to use that identity in a box, but in reverse. So we are going to call this matrix U. It's a unitary matrix and it has the form of a gauge transformation, except that it isn't really, because it's depending on some physical fields of the theory, not on gauge parameters. But it has the same form as a gauge transformation, and that's all that these expressions care about. So this I can use in that formula, and it tells me that d mu phi is equal to U inverse d mu A prime U phi. And sorry, so what I want to do actually is choose U to be opposite of this. U equals e to the minus I theta A sigma A by 2. Okay, so the first term here, U inverse, is e to the plus I theta A sigma A by 2. And here, what is U times phi? This is U, this is phi. So what is U times phi? Is sigma. So d mu sigma. Okay, now this d mu is still d mu prime. It depends on A prime, right, which is the gauge transformed A. But I can perform a gauge transformation which undoes that, brings A prime back to A. What will be the effect of that gauge transformation here? Nothing. So therefore, I can just forget about the prime. So d mu phi is that. Okay. Now, I put that fact in here, and this becomes, what does it become? D mu sigma dagger, d mu sigma. So everything is done. So let's write the full Lagrangian. It is equals minus 1/4 f nu a plus d mu sigma dagger I d mu sigma minus lambda sigma dagger sigma minus a squared by 2. This is everything. So where are the theta fields now? Are there theta fields in this Lagrangian? All gone. In one line, what happened? We parameterized phi to be this phase times this kind of vector, so this thing times this kind of vector. And because this is a phase having a form of a unitary matrix, it dropped out from this term. And because of the special form of the covariant derivative, which transforms by the same unitary matrix, it also dropped out of this term. So it's gone. Yes?
In the previous case, we had to make a gauge transformation such that the a mu minus e theta take
Yeah.
the theta gets saved. Here
It's the same thing. We've done the same thing, just in some different words.
So when we were
Yeah.
changing d mu prime to
Yeah.
d mu,
Yes,
like
that
we
was the
were
gauge
absorbing-
transform. That's correct. So you could say that changing d mu prime back to d mu was a gauge transformation which didn't affect f,
Okay.
and so I think that's the step.
Right.
Yeah, good. So this is it. This is over. So this is the correct Lagrangian for that, from where we should be able to read off all the properties of the theory. The only thing that's stopping us is that we have to work out d mu on sigma, and we have to also work out sigma dagger sigma, and the only thing we need to know from all of this is sigma, which is a two-component column vector that. So now let's do it. So first let's do the last term. Last term is easy. If that is sigma, then clearly sigma dagger sigma is nothing but 0, 1 by root 2 a plus sigma, 0, 1 by root 2 a plus sigma, and that's equal to half a plus sigma of x squared.
Sigma star.
Sigma is real. You forgot, but I
Yeah,
had
let's-
4 real components in phi, and I took 3 out by a phase.
Okay.
So sigma is real, and the point is that the fact that I can do that comes from two things. One, I can use an SU2 rotation to put the two-component field completely into its lower component, and still I can use another rotation to make it real, because SU2 being a complex group contains a U1 rotation, so I can actually take the complex number here and make it real. I remove the imaginary part, and after I do that, I've used up all the SU2 degrees of freedom, so I put e to the I theta ATA outside, which represents those degrees of freedom, and those are the Goldstone bosons. The would-be Goldstone bosons. Okay, so that's this. So now sigma dagger sigma is therefore half of a plus sigma whole squared, so I put that in here, and this I easily find to be minus lambda by 4 2a sigma plus sigma squared. Okay, a plus sigma whole squared by 2 minus a squared by 2. There's always this square which I keep forgetting, and then I take the 1 by 2 out, then it's a 4, and then a squared by 2 cancels. Maybe once it's out, once this 4 is out, then it's 2a sigma plus sigma squared. This is correct. So that term was easy. This term we never had to do anything with it. It's still whatever it always was, and we are never going to do anything with it. The gauge field, the Yang-Mills Lagrangian just is its own thing. It's not affected by our changes of variables on phi. This is the fun term. So now we finally need to deal with the question, what is d mu sigma? So I always write it as d mu sigma I, but it's actually del mu of sigma I minus Ig a mu in the matrix form J sigma J. This is what it is. So now I need to work this out. Well, now we should be happy that this is SU2. So A mu, by definition, as you know, is A mu A, TA, where TA are the generators. And those generators are sigma A by 2. And this is equal to, now what is this equal to? Well, you know the three Pauli matrices, 0, 1, 1, 0, 0 minus I, 0, and 1, 0, 0, minus 1. So if I dot A with that, I get the matrix half A mu 3 minus A mu 3, A mu 1 minus I, A mu 2, A mu 1 plus I, A mu 2. Good. This might be the first time that we actually unpacked the A matrix explicitly. It's just another way of packaging the three components of A, which are the SU2 triplet of A, which is the Yang-Mills field in components. They just get packaged into a matrix. Okay, good. Now I need to carry out this thing. So I'm trying to work out d mu sigma. So d mu sigma therefore is equal to I is equal to del mu of 0. So 1 by root 2, 0 and A plus sigma. Okay, because that's sigma, minus I times G over 2 times this matrix A mu 3 minus A mu 3, A mu 1 minus I 2, A mu 1 plus I, A mu 2 on 0 and A plus sigma by root 2. Okay? And what is this? 1 by root 2 is common. I take it out from here and from here. Del mu on this, A is a constant, so I get 0 and del mu sigma. There I do the calculation. I must do matrix multiplication of this on that. And so I get minus Ig by 2. Very unhappy about this 2. It wasn't there in my notes, so I don't know what is going wrong. Maybe I did something wrong. And then this times this in the upper one and this times this in the lower one. So A mu 1 minus I A mu 2, A plus sigma, and minus A mu 3 plus sigma. Okay? Root 2 is outside everything. Good. Yes, so this is my d mu of sigma. I can still simplify it further. Yes.
It was never defined with 1 by 2. Like
What was never defined with 1 by 2?
minus Ig by 2.
No, that's from the T. The TA are sigma A by 2. It's that too. Okay. So now I have upstairs minus Ig by 2, A mu 1 minus I A mu 2, A plus sigma. You should just remember that A is a constant, which is the vacuum value, and sigma is a field. And downstairs I have del mu sigma minus, or rather plus, Ig by 2 A mu 3, A plus sigma. So that's my d mu of capital sigma. Now I have to just take this and dagger it and multiply. Dagger is what? Just transpose and send all i's to minus I. Complex conjugation. Can't be very hard. So let's do it. So there's a 1 by root 2 from each d mu sigma and d mu sigma dagger. So there'll be 1 by 2 in front of everything. And then I have to take this thing daggered. So when I dagger it, it becomes a row vector and minus I goes to plus I. So the dagger is the row vector ig by 2 a mu 1 minus I a mu 2 plus I a mu 2 a plus sigma, and then the other entry is del mu sigma minus ig by 2 a mu 3 a plus sigma. So this is a 2-component row vector, and now I'll rub out a lot of stuff, and to be lazy, I'll just tell you that you have to dot this vector with this one, but this 1 by root 2 has already been taken outside. This is a row vector, that's a column vector. Just do the multiplication and you're supposed to get a single number, which is the Lagrangian term. So we get 1/2. Now ig by 2 minus ig by 2, so it's g squared by 4 a mu 1 plus I a mu 2. Okay, I should raise the index mu, or I should raise it in the other one. I just imagine that I raised it here. Okay, because this has the index up. So far so good. So I got this times this, so a1 a mu 1 minus I a mu 2, and then a plus sigma squared. That's from first entry of this vector times first entry of this vector. Now I do second one, plus del mu sigma whole squared, because this is of form a minus b a plus b. So it's del mu sigma whole squared and then this other thing whole squared, which is g squared by 4 a mu 3 a mu 3 a plus sigma squared. Is it looking nice? So first let's single out this. We get the correctly normalized Higgs field del mu sigma squared. I erased it now, but we had found a mass term for it. Do you remember from the last term? You forgot it. Okay, we'll bring it back. And what about all these? Well, this gives me a1 squared plus a2 squared plus a3 squared, all on same footing, g squared by 4 in front, and a plus sigma squared multiplied. So plus g squared by 4 a1 a mu a summed, and then a plus sigma whole squared. So this is the full d sigma dagger d sigma. There is nothing more. One real scalar field and 3 mass terms. Okay, so mass terms will come when we expand this. So this one, let me expand. So this is equal to half del mu sigma del mu sigma. Now these are 2 fields. This is also a field. So if I want to look only at the quadratic part, I should just keep this a squared. Then there'll be this a plus sigma is a squared plus 2a sigma plus sigma squared. But those are interaction terms. I'm not even going to write them. I'll just keep a squared. So I get g squared a squared by 4 a mu a. And now we can see our Higgs mechanism, because those are mass terms, equal ones for all the 3 Yang-Mills bosons, and the mass is Ga by 2, I guess.
So that would be g square by 8.
8. Always possible. Yeah, 8. So then the mass is Ga by 2 root 2. So mass of the A fields is Ga by 2 root 2. In my notes it's Ga by root 2, so this 2 is a bit, I have to sort it out, but I think it's maybe correct. Good.
There is like a plus in
N square
between, so it's a
Sorry.
imaginary mass, right?
Ga by root 2. 1 second, huh? Ga by 2. Yes, sir. What?
So because there is a plus sign in between the kinetic term in this one.
Yes.
So is it a negative mass?
No, we've been through this discussion, you have forgotten. With gauge fields, the correct mass term should have a plus sign because A mu A is equal in our choice of metric to A0 A squared minus AI A squared, and these are the ones which need to have the correct sign because it's the three space components which are going to be physical, not A0. We had a discussion long time back about massive gauge theory. You can now apply that discussion here. For example, with this form, you can calculate the equation of motion for the Yang-Mills field. You need to vary A mu here, and you need to vary A mu in the term I've dropped, minus 1/4 F mu nu, and you get the massive Yang-Mills equation. Okay, and from that equation, you will, at quadratic order, you will get a constraint that divergence of A mu is 0, and that divergence of A mu being 0 will enable you to remove one component, and it will be this one, and those will survive. And that's the correct, go back to the notes, you'll find it there. This is the correct sign for the mass term of A.
So that should make MA equal to Ga by root 2, right?
Okay, let's see. No, this is the same as m squared by 2. So m squared is g squared a squared by 4, so ma is Ga by 2. Yeah, good. Now what about sigma? That's the only thing that we've also done it, but we just erased it. So let's remember, we had a term minus lambda sigma dagger sigma minus a squared whole squared. This became minus lambda a plus sigma squared, this was by 2. Then it became this minus a squared, and this is minus lambda by 4 2a sigma plus sigma squared. And this, again I'm keeping only the quadratic term, comes only from the square of this, and this is minus lambda a squared sigma squared. And this is a correct sign mass term, and the mass of sigma is root 2 lambda a. So this parameter A determines the mass of sigma and the mass of A, but there's a slight difference. The Yang-Mills particle mass is determined by A and the coupling constant G, while this is determined by A and lambda. Lambda is the coefficient of the quartic term. Okay, it's lambda which is sort of mysterious, or was mysterious in the standard model, because G was the Yang-Mills coupling. So when people detected Yang-Mills particles, they already knew what is the self-coupling of these particles because they measured them. These particles are the W and Z. So this is like a toy version of the standard model where these three particles of that mass are like W plus minus and Z, three bosons. It's not exactly the standard model, and I think Arun will tell you in his course what is exactly the standard model, and those of you who don't take that course should definitely find out when he's going to do that and attend it. Notice, by the way, that our notation also took care of this. You see that A1 and A2 come naturally in a complex combination, and this is like W plus W minus, while A3 comes naturally in a real form, and that's like Z0. But these indices actually refer to the electric charge, and that's because the standard model has not only SU2 Yang-Mills but also a U1, and a combination of these two things. So SU2 cross U1 breaks to U1. That U1 is identified with the electromagnetic U1, and it's the photon. And then how these couple to the photon determines their charges. So I'm not going to do that here, but just to say that in a toy model like this, you have three bosons all with the same mass. In the actual standard model, only W plus minus have the same mass, and Z0 has a different mass. And that's because that model has another parameter besides G. Since it has SU2 cross U1 symmetry, SU2 has a coupling G, and SU2, the U1 has another coupling G prime. So you can vary them independently, and it turns out that these masses therefore depend on G and G prime in different ways, and that's how you get three particles of two different masses. But the point is that if you know this wave, and you certainly know this G, then you know the mass of these particles, but that's not enough to tell you the mass of this particle, the Higgs particle, because this knowing these two numbers does not tell you lambda. Okay, and that's the problem. That's why this was a mysterious quantity till it was found to be somewhere in the range of 120 GeV when the Higgs was actually discovered. And so in the end we have, so we've done everything and we found exactly what we expected. Yes?
So interaction term for sigma,
Yes.
it has a cubic term.
An aquatic term. An
Oh,
aquatic.
sorry.
Yeah. Cubic term from here, an aquatic term, again with correlated coefficients. Again, it's actually the same as the first model we did where there was a real scalar. It's basically the same structure. There's a cubic and aquatic term.
And this is like two different like circular polarizations for when you say
Yes, it looks like that. It's not really that because no, that's not true. It's because this 1 and 2 and 3 are in the SU2 field space, not in physical space.
Oh, right.
So they are like circular polarization. That's the structure of SU2. SU2, though in principle its three directions are all equivalent, J1, J2, J3. But whenever you pick one of them, and that's why in all quantum mechanics we pick the Z axis, then with respect to that chosen one, the 3 behaves differently and the 1 and 2 combine in naturally into some kind of phase in that group space, not in physical space. Here, of course, it's actually in the end all symmetrical. So it's just that the calculation in a natural way brings out these combinations. But when you do the standard model, then actually you get a complex W plus and W minus, and you get a real Z. So Z is its own antiparticle, while W plus and W minus are each other's antiparticle. Yeah. So this is the complete story of SU2 with a fundamental, with a Higgs. So now there is a notational thing. We started with a field phi. People also call that the Higgs. They say SU2 with a Higgs in the Higgs doublet. That's what we have, a Higgs doublet, the original phi. Okay, so there's the Higgs, the doublet, the scalar field you put in at the beginning is called Higgs. The scalar field you get at the end is also called Higgs, but they're not really the same. I mean, this is part of the original, but it's one field. Those were, so people say standard model has a Higgs doublet, which has 4 real components in it. 3 of them are eaten by the Yang-Mills particles to become massive, and one is seen experimentally as the Higgs boson. And that's what we've done. So don't get confused if people call the original phi as Higgs also. It's not actually the particle, it's the field that you started with. We always have to start with some field which gives us the sort of a priori structure, gauge structure of the theory, and then with this broken, spontaneously broken potential, we just do calculations almost blindly till we get a final form where the actual excitations of the theory are manifest. They are simply hidden in from the beginning. It's the same Lagrangian as we started with. We didn't change it. The same. We just expanded around the minimum. And we did that intelligently by parameterizing phi with that e to the I theta ATA times that thing. That parameterization was key to a very simple answer where basically phi d phi dagger collapsed into d sigma dagger, and phi dagger collapsed into sigma dagger. So all the thetas went away very readily.
Initially, phi was not having any mass.
Initially, phi was having a mass of the wrong sign, because you forgot
that
the
is
potential of phi was this.
But that was imaginary. Like,
Yeah, wrong sign mass. But that's always that's what a spontaneous breaking potential is. It always has to have a wrong sign master.
but that is not measurable. Like,
That's
after
not
breaking-
measurable
yeah.
because that's not the mass of the excitation. That's the mass of the original classical field. It has no physical meaning. Its only job is to create spontaneous symmetry breaking by moving the minimum away from the origin. And it is in this language, it is lambda a squared. So if you take the cross term, it's plus lambda a squared phi dagger phi. And that's the wrong sign mass term that we started with. We just call it a mass term. You're right, it has no physical meaning. In fact, the final mass is not even that, it's root 2 times that. Okay, so I'll stop here. And we are done with Higgs mechanism. From next week, we'll start on something a little different. So, any questions? Yeah.
Is there spontaneous breaking for vector fields?
Vector fields. So yeah, good. So you could ask first, why don't we have spontaneous breaking induced by either by fermion fields or vector fields? And the point is that we gave phi a vacuum value, right? Phi took a vacuum value. Now physically, if a fermion takes a vacuum value or a gauge field takes a vacuum value, that value can't be Lorentz invariant, because these are fields that transform under Lorentz transformations. So imagine a vector field A mu takes a vacuum expectation value, then that value is a 4 vector, constant 4 vector. It has to be constant by translation invariance. So a constant 4 vector, if I expand around that, the theory will no longer show Lorentz invariance. If I try to expand around a spinner, then there'll be a constant spinner, and it'll also be anti-commuting. So I'll have expanded my theory around something which will again show breaking of Lorentz invariance. But if a scalar takes a vacuum value, that's not a problem, because a scalar can be a number, and that number is the same in all Lorentz frames. However, there are fermion theories where people postulate that the pair psi bar psi takes a vacuum value. Psi bar psi is a scalar, even though psi is not a scalar. And actually, you might have heard that in superconductivity, Cooper pairs condense. That's the same statement as saying psi bar psi, where it's, or psi psi, which is a composite of electrons. That's a scalar, and that condenses. So it's always a scalar that condenses. And in fact, superconductivity is an example of Higgs mechanism. And I'll get somebody, as I said, to talk about this sometime.